Welcome everyone to this MIDAS seminar. I am H.V. Jagadish, the director of MIDAS. I am delighted to introduce today Arya Farahi, who is a postdoctoral MIDAS data science fellow. He has actually been a major contributor to many aspects of data science at the University of Michigan over the past many years, starting from work that he led with the Michigan data science team during the Flint water crisis and continuing on in a number of different interesting ways over the years. Today, though, he's going to be talking to us about algorithmic trustworthiness and specifically the KiTE framework that he has developed. And I look forward to your presentation, Arya.
Yeah, thank you, Jack. All right, thank you, James. Thank you, Jack, for the introduction. I'm very excited to give this presentation and introduce KiTE. This is a software package that Danai Kutra and myself, we are developing, and this is a framework to perform algorithmic fairness and quantify and assess how much trustworthiness we have in our predictive model. So in this talk, I'm going to focus on the theory behind KiTE and showcase some of these applications. And if you are interested in using KiTE, just feel free to reach out and I'm happy to provide the code to you. So before jumping into my talk, so let me just take a step back and give you a very broad overview of my research. So my research both contributes to the theory and applied sides of data science. On the theory side, I'm mostly interested in developing a better understanding of the limitations of AI systems, especially when we want to deploy them into the real world settings. And on the applied side, I'm mostly interested in the applications of AI and Bayesian inference solutions to problems in survey astronomy and urban decision making, which I'm going to talk about all aspects of my work in this presentation. I'm also very interested in the computational aspect of data science. And so far I have released 3 different software packages. 2 of them are performing regression analysis and population analysis. And 1 of them is doing hypothesis testing. But today I'm going to talk about KiTE, which has not been released yet, but I would be more than happy to provide the code to you if you find it useful for your research. All right, I'm going to start this presentation with an introduction to some of the projects that we are doing with the city of Detroit. And then I'm going to use this project and motivate why we want to look at the fairness and trustworthiness of predictive models. Then I'm going to talk about the theory that we developed to quantify the trustworthiness of predictive models. Then actually I'm going to apply this method to some of the problems that we have in survey astronomy. And I'm going to talk about how we can use these methods to shed light on modeling biases that we have in astronomy and push the boundaries of the scientific discovery. And then I'm going to come back and talk about some of the other projects that I have done and talk about future direction. All right, in early 2020, before pandemic starts, Danai Kutra and myself got together and co-founded Michigan Data Informed Cities for Everyone. So the idea behind this research collaboration is to partnering with the city governments and nonprofits and develop data-driven solutions to some of the emerging challenges they have in their communities. And the overarching goals of our partnerships are to provide AI support solutions to inform budget planning, resource allocation, and policy evaluation. So far, we have started this project with a 3-year research agreement with the city of Detroit, which is facilitated with MIDAS. And currently, since the beginning of this collaboration, we launched 3 different projects with the city of Detroit. And so far, we have 1 faculty member who is Danai Kutra on our team. We have 2 postdocs and 10 students who are contributing to different aspects of our project. Today, I'm going to talk about one of these projects that I'm currently leading with MIDAS. In this project, the city partnered with us to develop a recommendation system to prioritize the road that need to get fixed. in the city of Detroit. And probably this is not very shocking to you, that city of Detroit is one of the worst cities nationwide in terms of its roads condition. So for example, here I'm looking at the percentage of roads which are in poor condition, and I'm comparing 3 different cities. City of Detroit, we are looking at the number which is around 58%. And I'm comparing this number with the city of Ann Arbor, which is around 28%, and city of Austin in Texas, which is around 18%. So here you can see that there is a huge discrepancy between other cities that we have and city of Detroit. And nationwide, this number is around 20%. So now we want to bring the numbers in the city of Detroit to be more consistent with the nationwide numbers. But as again, it is probably not very surprising to you, there are a lot of challenges. The city does not have enough resources to fix all roads which are in poor condition simultaneously. Now we are thinking about, and one of the time consuming and expensive tasks is how to quantify the condition of each road. We have to hire someone, send that person to the location of this road. That person needs to perform some measurements, and then we can say whether it is in a poor condition or good condition. Now we are thinking to develop an automated system to quantify the condition of these roads based on a lot of images that are collected by the city. So to start this project, the city collected around 4 million images, and every 6 months they are planning to get a new set of images. And hopefully by developing a recommendation system for them, we are going to save time and money and reduce human in the loop. So we divided this project to 3 different tasks. In the first task, we are developing a classifier. We take all of the raw images, and our classifier identifies cracks and potholes across the city and measure the properties of these cracks and potholes. Now we can look at the distribution of cracks and potholes, how this is distributed across the city. And because every 6 months we get a new set of images, now we can see how these cracks and potholes degrade over time. Now we can use all of these informations and probabilistically say whether a piece of road is in a good condition or whether it is in a poor condition. And then we are going to pass this information to a recommendation system that Eric and Sijun are designing for us. In this recommendation system, we are going to combine this information with some socioeconomic data, occupancy data, some public assets which are owned by the city, traffic volume data, and perform some cost-benefit analysis. So the idea is that we cannot fix all of the roads which are in poor condition simultaneously. We have to prioritize which roads we have to fix first. So we want to provide the maximum benefit for the residents. And now we are combining all of this information to perform cost-benefit analysis and find and identify the roads that if they get fixed, they provide the maximum benefit. And then Hongo is designing a UI system for us to summarize and visualize the results to guide resource allocation and budget planning for the policymaker. And hopefully down the road, ultimately they are using this UI system to make their final decision. But there are a lot of challenges in designing an AI system and deploying them into our community. And there are a lot of discussion within and outside of the community about the implications of the AI system on our society. And we have seen news and headlines and examples on how algorithms have negatively impacted the underrepresented population. So it was very important for me initially in the project to think about the potential fairness implications of this AI system that we are developing and how it might impact the life of residents. For example, here in the bottom, I'm looking at the average road quality for different census blocks, and I stratify the census block based on the poverty rate and household income. So here you can immediately see that the poverty rate and household income of your neighborhood determines what type of road condition you have in your neighborhood. And this is exactly the type of situation we don't want to be at. So we want to make sure that the AI system that we are developing, if it is going to be deployed by the decision maker and is going to be used by the decision makers, it is not going to exacerbate this type of biases that we are seeing in the historical data. And actually, we want to see that this type of biases is going to go away once they start to use our recommendation system. All right, now we have to understand what are the potential sources of bias and then develop strategies to mitigate these sources of bias. The first source of bias can come from the task. First, we have to identify a task or ask a set of questions, but these tasks that we are designing and the question that we are asking, maybe they are not fair by construction, or maybe the objectives are biased by construction. So we have to be very careful about the task that we are designing. Another important source of bias comes from data. Data are not always clean. Data can be noisy. Noise can be correlated with the protected features, or it can be sampled in a biased way. We can have missing values. This missingness can be correlated with the features that we have in our data. So we have to understand all the limitations behind the data and model all of these limitations to make sure that we are providing trustworthy information to the decision makers. Predictions of machine learning and statistical models are not perfect. Always they make mistakes. We have to quantify the rate of mistake and understand the uncertainty behind the predictions of these models. Otherwise, giving just point estimation without providing any uncertainty on them is not going to be very useful for the decision makers. But a central part of any AI system is the models that we are deploying into them. A decision maker is essentially going to use the output of our model or the information that is provided by our model to make their decision. So it is the job of us or the modelers to guarantee that the information that we are passing to the decision makers are trustworthy. If the information that we are passing to the decision makers are not trustworthy, it is impossible for them to make a fair decision. So the first step toward algorithmic fairness is to make sure that our models are providing trustworthy information. This is a necessary condition, but this is not a sufficient condition. And in this talk, I'm going to talk about how we can quantify the trustworthiness of algorithms, and especially predictive models. And I'm going to mostly focus on probabilistic classifiers. All right, so let me give you another example. Let's imagine that we have a classifier that predicts the probability of developing cancer for a set of patients if they are given a treatment T. Now let's imagine that after training, for a subset of patients, this model is going to predict that with 50% chance, they are going to develop cancer. So if this prediction is trustworthy, it suggests that for a subset of patients, they have to develop, 50% of them have to develop cancer. If this number is 60 or 40%, it suggests that this model is not trustworthy, or in another word, it is not calibrated. All right, now let's imagine that this subset of patients consists of 10% from a minority group A and 90% from a majority group B. Then we have to run an observational study to find the frequency of developing cancer among our patients and say whether this information is trustworthy or not. And in our patients, we find that 95% of people in group A and 45% of people in group B have developed cancer. If we do the math, actually we find that on average over our population, 50% of people have developed cancer. So this one suggests that the prediction of our model on average over the population is trustworthy. This is a good news. But if we are concerned about each individual subgroup in our data, then this model is not trustworthy anymore. Or in another word, it is not group-wise calibrated. And the impact of this type of miscalibration can be more devastating for the underrepresented population, because the prediction of the model from the actual observation for the minority population is much larger than the majority population. Again, if we go back to our hospital and clinical setting, we want to distribute resources among our populations based on their needs. We don't want to exactly assign the same priority to every single patient and provide them exactly the same type of resources. So the first step toward making fair decision is to make sure that the information we are providing to the decision maker is trustworthy for every single patient in our hospital, not by averaging over all of our patients. And this problem of calibration is actually not a new problem. People started to look at the calibration of their models since 1962. And very recently, some authors started to make connection between the problem of calibration and algorithmic fairness. As I argued, the first step toward algorithmic fairness is to make sure that we are providing trustworthy information. But what are the challenges? So there are two key challenges that we are trying to solve. One is how to perform hypothesis testing to say whether a model is group-wise calibrated or not. For example, we have access to a lot of different test scores, like accuracy, precision, confusion metrics, AUC, Breyer score, that we can use to compare the performance of two different models, but they are not sufficient to perform hypothesis testing, to say which one of these models is group-wise calibrated and which one is not. And if we know that a model is group-wise miscalibrated, how to quantify how much bias we have in a prediction of a model, especially when we go to a high-dimensional setting. So we address both of these challenges with our new package, which we call it KiTE. It is a kernel AI trustworthiness examiner. It is an open source code that performs trustworthiness quantification. So the first step, it is going to do hypothesis testing and say whether a model is group-wise calibrated or not. And in the second step, it is going to perform calibration. If you give me an untrustworthy model, I'm going to estimate the biases and I'm going to correct for those biases. All right, first I'm going to talk about how it is performing hypothesis testing, and then I'm going to talk about how it performs calibration. So in my hypothesis testing framework, I'm assuming that I have a test sample for which I know the label of data sets. And I have a trained model that is going to make a probabilistic prediction. All right, now we have to mathematically define what exactly we mean by group-wise calibration, or in another word, local calibration. I'm going to use local and group-wise calibration completely interchangeably. They mean exactly the same thing. Model F is group-wise or locally calibrated if and only if the prediction of this model matches the frequency of future observation for every subset of our population. This is as opposed to global calibration. Model F is globally calibrated if the prediction of this model matches the frequency of future observation by averaging over the entire population. So here you can see that group-wise calibration or local calibration is a much stronger constraint. And to achieve the goals of algorithmic fairness, trustworthiness, we have to show that the model is locally calibrated, and showing that the model is globally calibrated is not sufficient. All right, but another important feature of this definition is the fact that input of the classifier doesn't need to be identical to the feature set on which we want to test the calibration of the model. For example, we want to predict the likelihood of developing cancer, and the input of this classifier is age, genomic expression, and gender of our patients. But a doctor or practitioner comes and say that, okay, I want to use this model in my clinical setting and make some decision about my patients, but I have to make sure that this model is trustworthy with respect to age, gender, race, and income level of my patients. If it does not provide me trustworthy information with respect to all of these 4 features simultaneously, I cannot use the prediction of this classifier. I don't care exactly what goes into the classifier. So there can be an overlap between X and Z, but they don't have to be identical. But theoretically, if we imagine that they are identical, it has some interesting additional theoretical consequences. First, a locally calibrated model is going to be equivalent to the true a posteriori distribution of our data, which implies that it has a unique solution. And this solution is going to be the optimal solution in the sense that it minimizes the Bayes error. So if we can show that the model is locally calibrated and X and Z are identical, then we cannot improve the performance of our model by hyperparameter tuning, by changing the model class or the way that we are performing optimization. We have achieved the best optimal solution. So let's say that I have a random forest and I trained it and I have shown that it is locally calibrated. By changing it to a neural network, I cannot change the performance of this model any further. And it can be used to perform goodness of fit. A miscalibrated model is not a good fit to the data. So now we can make all kind of connection between this model and the statistical literature. All right, so now we have to identify a test statistic and use this test statistic to perform hypothesis testing. So probably I have only 2 equations in my talk, and this is only one of them. So a model F is going to be locally calibrated if expected local calibration error is exactly equal to 0. How this test statistic works, basically we compute the rate of error for our classifier and multiply it by kernel function that takes the feature and the model prediction and take them into a feature space, into the kernel space. And by computing the expected value, we can get our test statistic. All right, in this case, we are assuming that our null hypothesis is that model F is locally calibrated on feature set X. So now our goal is to reject this null hypothesis or accept it. But because we are in a finite sample setting, we have only small samples, for example, in our hospital setting, that we know the labels, we have to quantify the null distribution. So we quantify the null distribution, we estimate our test statistic for our data and ask whether it is consistent with our null distribution. In that case, we cannot reject the null hypothesis and we can say that our model is locally calibrated. Or if it is much larger than the null distribution, we can reject the null hypothesis. Essentially, we want to quantify the p-value or the probability that the observed test statistic is larger than the null distribution. All right, so I'm going to show you how it is performing in a simulated setting. Then I'm going to apply it to some real-world data set. So in my simulated setting, I assume that I have a 2-dimensional feature space and labels are drawn from a Bernoulli distribution. And the mean of this Bernoulli distribution comes from a sigmoid function of x1 and x2. So this sigmoid function of x1 plus x2 is my true model or a locally calibrated model. Then we can identify one locally miscalibrated model by dropping one of these features, or a globally miscalibrated model by adding a normalization and a slope to one of these features. Then we are going to draw 2000 random pairs of data from this generative model and ask whether our test statistic can distinguish between these 3 models or not. All right, so this is a type of plot that I'm going to show you throughout this talk a lot. On the top, I have the value of my test statistic, and in the bottom, I have the p-value. If the p-value is very large, we cannot reject the null hypothesis, and this model is locally calibrated, or it is trustworthy. So in this case, our blue model is trustworthy based on our test statistic. And the other 2 models, we can reject the null hypothesis, and we can say that they are miscalibrated. But if we look at the value of our test statistic, we can quantify how much untrustworthiness we have in our data. For example, the orange model is less untrustworthy compared to the green model. Now we can perform all kinds of model comparison. If you give me 2 different models, I can use this test statistic to say which one of these 2 models are less untrustworthy compared to the other one. All right, now we know that the majority of machine learning models are going to be group-wise or locally miscalibrated. So we have to develop a mitigation strategy and calibrate an untrustworthy classifier to make them useful for our clinical setting or other settings. And there are a huge number of calibration methods proposed in the literature, but unfortunately, all of these calibration methods are concerned about global calibration. They want to make sure that a classifier, on average over the entire population, give us trustworthy information. But as I said, this is not good enough to achieve the goals of algorithmic fairness and trustworthiness. We have to make sure that the model is group-wise calibrated. So this motivated us to develop our own calibration strategy. So in this setting, we are assuming that we have a calibration sample. Again, for this calibration sample, we know the label of data sets. We have a trained model, and this trained model takes this data and make a probabilistic prediction. Now we want to change the prediction of this model in a way that for the new model, it is going to make unbiased prediction, or the prediction of this model is going to be locally calibrated. So actually our model is very simple. We are saying that, okay, we can take the output of classifier and just add an additive bias to it. And this additive bias is a function of feature set on which we want to calibrate our classifier. And the goal is to estimate this additive bias. How we are going to estimate it? We are going to use the information that is provided in the calibration sample to estimate this additive bias. And the sum of these two quantity is going to be a new classifier that is going to be trustworthy or group-wise calibrated. All right, we have proposed an estimator for this additive bias. Essentially, it is computing the rate of error of our original classifier for the sample that is provided in our calibration sample. It takes the feature again and take them into the feature space. And now we can estimate the additive bias for each individual new instance of data. For example, if a new patient comes to our hospital. Now we can estimate the additive bias for at the individual level, all by taking average over subpopulation of our data, we can get group-wise biases. All right, so if I take this calibration strategy and apply it to my simulated setting, actually we can show that the p-value goes away from 0, which suggests that now our model after this applying this calibration become locally calibrated. But if I take one of the methods of global calibration, it cannot achieve the goals of local calibration. So these methods are not sufficient to achieve the goals of algorithmic fairness and trustworthiness, but we have shown that in our simulated setting, we can use this estimator and this model to achieve the goals of algorithmic fairness and trustworthiness. So let me pause here and take any question, and then I'm going to move on with the next part of the talk, which I'm going to talk about how we can use this method to shed light on some of the problems that we have in astronomy.
Let's see, and we do have one here from Shelby Cox. How do you determine the possible biases of your model?
So the possible biases of our model is coming from the calibration sample that is provided to us. So we have to run for example, in our clinical setting, we have to run an observational study and identify the true label of our data set. Now we have a trained model and we have true labels for a subset of our population. We are going to use all of those information that exists in our subpopulation for which we have the labels and estimate the bias. Without having this calibration sample for which we know the label of data set, it is impossible to estimate bias. But once we have some label sample, we can use this information to estimate bias. I hope this answers your question. All right, so now let's see that how we can actually use this model and push the boundaries of scientific discovery. So one of the key questions that we are concerned in modern cosmology is what are the properties of dark matter and dark energy? So by looking at the universe, we realize that only 5% of the energy budget of our universe comes from the normal matter that we see around us. The rest of it comes from dark matter and dark energy. Dark matter is this hypothetical matter that interacts with normal matter through a gravitational channel. But because it cannot emit any light, we cannot directly observe it. We have to rely on the gravitational properties of our universe to infer how much dark matter we have and what are their properties. And the other one, which is even more mysterious, is dark energy. We think that dark energy is intrinsic property of our space-time that causes expansion rate of our universe to accelerate. All right, but since they discovered around like 4 or 5 decades ago, theorists started to develop theoretical models to explain the properties and origins of dark matter and dark energy. And today we want to use observational and experimental data to construct the properties of dark matter and dark energy and see which one of these theoretical model matches our observational data better. For example, in the bottom, I have a very small subset of theoretical models that are proposed to explain dark matter. Now we want to see which one of these theoretical model matches our observational data better. The first step, we have to identify some cosmological probe. What objects we can use to reconstruct the properties of dark matter and dark energy. One of these probes is galaxy clusters. So by looking at the sky, we realize that galaxies are not actually randomly and uniformly distributed on the sky. Typically, they are clustered together. Today, we know that these galaxy clusters are living inside dark matter halos. So most of the mass of these dark matter halos come from dark matter particles that are not directly observable to us. These dark matter particles provide a potential well, and these galaxies fall into this potential well and become gravitationally bound to each other. So really, when we are looking at this galaxy cluster, we are looking at a bunch of galaxies which are gravitationally bound to each other. All right. Then we started to perform numerical simulations to see how these galaxies inside these dark matter halos interact with each other. And we realized that the number density of dark matter halos in our universe as a function of the mass of these dark matter halos and how this number density evolve as a function of time is super sensitive to the properties of dark matter and dark energy. So essentially now we want to go back to our observational data, identify a set of galaxy clusters, and then measure some of their observables. For example, we can estimate how many galaxies are sitting inside these dark matter halos. And then we can use these observables, map them to the mass of the host dark matter halos, reconstruct the number density of the dark matter halos in our universe, and then we can estimate the properties of dark matter and dark energy. And today, more than 10 experiments are proposed and designed to study the properties of dark matter and dark energy using galaxy clusters. One of these experiments is the Dark Energy Survey. Actually, University of Michigan is one of the active members in this specific survey. So the idea behind this survey is to take the images of the sky. We are taking images of 1/8 of the entire observable sky. It is a 5-year program, and the data collection is ended in 2019. Now we are reducing the data. We are identifying galaxies in our data. We want to run our cluster finding algorithm and perform a cosmological analysis. And we are hoping that by the end of year 5 data, we are going to find 30,000 galaxy cluster in that small patch of the sky. All right, but since we got the first year data, we started to perform some preliminary analysis, and it was very puzzling for the community. So here on the y-axis, I'm looking at the quantity that is called S8. S8 is actually a combination of 2 different quantities. One of them is sigma 8, which is basically amplitude of the quantum fluctuations left over from our Big Bang. And the other one is omega m, which determines how much dark matter we have in our universe. The combination of these 2 quantities is called S8. So we can use the population of galaxy cluster to estimate this quantity, or we can use other probes such as CMB. CMB is the cosmic microwave background. By looking at the fluctuations in the cosmic microwave background, we can again estimate the same quantity. And the result that we are getting from these 2 different experiments are significantly different. So this suggests that maybe the models that we are using are not correct, or maybe there is a new physics that we are not putting into our model. So this can come from the biases in the data or biases in the way that we are interpreting our data, or maybe this is a smoking gun for a new physics. Before making claim that we made any new discovery, we have to make sure that the way that we are interpreting our data and the way that we are modeling the data is not biased. All right, to understand the sources of bias, first we have to understand how these cluster finding algorithms work. So we are working with the cluster finding algorithm that is called RedMapper. So this algorithm basically looks for the overdensity of red galaxies on the sky. You can think of just a Gaussian mixture model. First, it identifies the central galaxy, because the properties of these central galaxies are very different from the properties of random galaxies that we see on the sky. They are typically more massive, they are much brighter, and they are much redder compared to random galaxy population on the sky. Once we find a central galaxy, we are going to assign a membership probability to each galaxy around the central galaxy. So basically, this membership probability determines with what probability these galaxies are gravitationally bound to the central galaxy. And then by summing over of this membership probability, we can get an estimation for how many galaxies are sitting inside this invisible dark matter halo. And then by using this quantity that we call it optical richness, we can get an estimation of the mass of the host dark matter halo. So here you can immediately see that if the membership probabilities are biased, then the estimation of optical richness is going to be biased. If the estimation of optical richness is biased, the estimation of mass is going to be biased. Then we are going to get a biased estimation of the number density of these dark matter halos, and the cosmological parameters estimated by using this observable is going to be biased. So again, we have exactly the same problem. We want to make sure that this membership probabilities that is assigned by this classifier is trustworthy. Or in another word, it is locally calibrated. But because initially we didn't have the technology to calibrate these membership probabilities, we said that, okay, we can forget about this observable and we are going to directly calibrate this optical richness. We generated a lot of simulation. We start from a dark matter halo. We populate it with galaxies. We put this dark matter halo on a simulated sky, run our cluster finding algorithm. Then we know, because we are inside the simulation, we know how many galaxies we put inside our dark matter halo, and we know how many galaxies measured by our cluster finding algorithm. So now we can reconstruct this probability distribution, and we can incorporate this information in a Bayesian way in our inference model to correct for the potential sources of bias. But this model is not sufficient because there might be untrivial correlation between this membership probability and the mass of the dark matter halo and other properties of galaxies, which cannot be captured by this first order approximation. And these membership probabilities actually are physically meaningful. They give us a lot of information about galaxy formation physics. So really, we want to go back to the origin of this problem and calibrate these membership probabilities. So we started to do that back in 2015 and 2016. We collected some observational data. We looked at some simulated data and said that let's make these membership probabilities calibrated. So here on the x-axis, I have the membership probability that is assigned by this red mapper algorithm. And on the y-axis, I have the true fraction of these galaxies that belong to the same dark matter halo. And initially, you can see that it is miscalibrated. It is not following the unity line. After performing calibration, then it is going to follow a unity line. But again, this method is not sufficient for many questions that we want to ask, because this one ensures that these membership probabilities are globally calibrated. But it is not going to remove all of the potential local miscalibration that we have in our membership probabilities. All right, I said that I have this method. I can apply it to this data set to see what happens. So Johnny Stevens, who is one of the PhD students in physics department, is developing a new version of this red mapper algorithm. I asked him to run his algorithm on a simulated data set. And in the simulated data set, we know whether these galaxies belong to the dark matter halo or not. So we get an estimation of probability from his algorithm. We have a true fraction of galaxies that whether belong to the dark matter halo or not. So initially, we observe that they are not globally calibrated. And if we perform our hypothesis testing, we see that the value of our test statistic is pretty large and the p-value is close to 0, which suggests that these membership probabilities are locally miscalibrated. After performing one of the methods of global calibration, we can globally calibrate these membership probabilities, but still after performing hypothesis testing, we find that there are some residual miscalibration. The p-value is close to 0, and the value of our test statistic is much larger than 0. So it suggests that there are some local miscalibration that couldn't be resolved with this method of global calibration. I said that I have my own method. Let's apply it to this data set to see what happens. Now, after applying this local calibration method, we can achieve the goals of trustworthiness. We can show that now the membership probabilities are locally calibrated and trustworthy. The p-value is much larger than 0, and the value of our test statistic is very close to 0. Now the question is that after debiasing these membership probabilities, can we resolve this discrepancy that we see in the observational data or not? Still, we don't know the answer because still we are working on a year 5 data, and there are other pieces into our inference algorithm that we have to make sure that other pieces are unbiased as well. So still we are working on the data, and hopefully in a year from now, we are going to have answer whether we have made a new discovery or everything was because of the way that we interpreted our data. All right, so in this talk, I spent a lot of time to talk about why we need to look at the algorithms, not only from a lens of accuracy and the rate of error, but also from a lens of trustworthiness. But as I argued in the first part of the talk, there are other sources of bias, which can come from data or can come from the prediction of our data. I have done a lot of work to model the limitations behind data. Data can be noisy. The data can be biased from the underlying can be biased and can be drawn in a biased way from the underlying population. So I have developed a lot of Bayesian algorithms to correct for this type of biases. And actually one of these works led to discovery of the anti-correlation between hot and stellar content of dark matter halos. And I have released a few software packages which are basically designed to handle noisy input data and perform population analysis. I would be very excited to talk about all of these packages and algorithms if you have any applications for them. And the other thing that I am thinking a lot about is how to quantify the prediction uncertainty of machine learning model, especially deep learning models, because we are going to use these deep learning models both to make scientific discoveries and to deploy them into our society. And getting a point estimation is not sufficient for many, many applications. We have to understand how much uncertainty is attached to these predictions. And there are a large number of methods that can estimate these uncertainties, but it is not obvious that always they are going to give us trustworthy uncertainties. Now we are developing methods to quantify these uncertainties and make sure that these uncertainties are unbiased and trustworthy. All right, so I hope that I convince you that KiTE is a very important package. It is a computational tool that allows a user to quantify the trustworthiness of probabilistic classifier, quantify group level and individual level biases that you have in your model, and correct for discriminatory information that is provided to your by your model. So to achieve the goals of algorithmic fairness, we have to make sure that our models are trustworthy. And one way to make sure that your models are trustworthy is to use this package. Again, I'm more than happy to provide this package to you if you have any applications for that. Just feel free to reach out to me. Now I am happy to open the floor for questions. Thank you.
So while we wait for other questions, let me ask you one, Arya. There are many different ways in which one can measure bias and many different ways in which one can be worried about fairness. You've described very interesting work in terms of finding out particularly where there's group level bias, and there are substantial differences in the model performance across groups. If I use KiTE as a computational tool to solve that particular problem, basically my question is, what happens for all the other problems that are not within the scope of your work? Is there a plug and play with some external system, like Weka or something like this, or is it that I have to, from a practical perspective, I have to go get KiTE, get system X, get system Y, get system Z, and try and work with each of them independently?
It is a very good question. So one thing that is important about the KiTE, it is just a performance metric. It is like AUC or accuracy. We can use it to quantify basically how much untrustworthiness we have. But it is not going to address the problem of algorithmic fairness. It is not going to tell us whether our algorithm or decision-making process is fair or not. That is coming at the next level. Because first we have to make sure that the information that we are passing to the decision maker is trustworthy. And then what the decision maker is going to do with those information is up to the decision maker. So for example, the decision maker can say that I want to equalize the false positive rate among different groups. So they are going to make a different decision. But maybe someone say that, okay, I wanted to make sure that I'm going to achieve the highest accuracy. So they are going to make different decision. That one is algorithmic fairness actually happening at the decision-making level. It is not happening at the modeling level. So here I am really worried about the information that we are passing to the decision maker. But it is up to the decision maker to make sure that they are making fair decision. And KiTE is not going to guarantee that the decision maker is going to make a fair decision.
Right, of course.
These are completely two separate issues.
Right.
But the first step toward making fair decision is to make sure that the information.
To have the knowledge, yes.
Yes.
And I think that that's a very important distinction, and I'm glad that you got a chance to remind us all about it. While we were talking, we've got several questions in the Q&A panel. So I don't know if you can press it on your computer. You can read it yourself, or I can read it for you.
I think I can read them. So does local calibration imply fairness, trustworthiness, or are there other metrics one need to consider? So for the trustworthiness of probabilistic classifier, it is going to guarantee that the information that you are passing to the next layer of decision making is trustworthy. But it does not solve any issue about algorithmic fairness. It is not going to guarantee that your decision maker is going to use those information to make a fair decision. So now at that level, you have to look at how the decision maker is going to make their decision, and then develop a test statistic or performance metric to make sure that you are satisfying the goals of algorithmic fairness in that specific problem. And different problems have different fairness issues. You want to look at what type of metric you want to use to check that whether that decision is fair or not. But it is not going to guarantee that those decisions are fair. So in order to use this tool to evaluate biases, are you required to have a good knowledge of what is the subgroups are? So you have to identify on which feature sets you want to quantify this trustworthiness. For example, in your medical setting, you say that, okay, I wanted to make sure that the information is trustworthy with respect to age, gender, income level, and other properties. So this one has to come from the user. The algorithm is not going to decide which feature you want to choose. You as a user have to choose which feature you want to check the performance or trustworthiness of your model. And can any model be locally corrected without retraining? Yes, so I'm assuming that the model is completely black box, and this is an auditing tool actually for the decision maker. So they don't have access to the model, and they don't know exactly what is happening inside that black box. We are saying that we are getting the output of that black box, and we are going to change the output of that black box by the information that is provided in our observational study to correct for additional biases. So really, you don't need to train your algorithm from the scratch, or even you don't need to know what happens inside your algorithm. And this is exactly the case for many medical applications or applications in our government, because they are asking a third party to design a model for them. So they don't know exactly how they train that model and how this model handed to them and what is happening inside that model. So you want to take that model and make sure that this model is passing trustworthy information. So initially, you don't need to know what happens inside that model. I hope this answered your question. When removing the bias, in the dark energy example, the p-value gets raised. Does it imply a trade-off between the fairness and significance? So honestly, in the dark energy example, we don't have the problem of fairness. Here, we want to make sure that the probabilities that we are providing, the probabilities that we are using to estimate the number of galaxies is unbiased estimation of the actual probabilities. So the fact that p-value rises is a good thing because we want to make sure that your model is consistent with the locally calibrated model. So this one ensures that those membership probabilities are unbiased estimation of the actual probability, which we can use to estimate the number of satellite galaxies. Are you saying a model can be both trustworthy and unfair? Yes, sure. A model can be trustworthy, but a model cannot be fair or unfair. It is the decision maker. The decision maker have to make a decision based on this information, and then the decision maker is going to make a fair or unfair decision. The model itself, I don't think you can say that the model is fair or unfair. Always the fairness is happening at the level of decision making. Without making any decision, basically it is very hard to say whether you are fair or unfair because nothing happened before that level. In the case of your astronomy application, how did you avoid the assumption in your simulation from having an impact on your result? So this is a very good question, and this is something that we are investigating because when we are performing simulations, we are not guaranteed that the simulated universe is identical to the universe that we have in the real world. So we have to make sure that the results are generalizable to the observational data. And this is exactly the type of questions that we are asking in astronomy. So basically, one way to address this question is to train it in one simulated universe and change the underlying properties of our universe, generate a bunch of different simulated universe, and make sure that the result that you are getting from one simulation is generalizable to other simulations as well. In that case, probably you can generalize it to your own universe. But answering this question specifically to our universe is a very hard problem. That's probably every day we are working on that, and it doesn't have any simple answer. Could local correction be integrated in the loss function of some model in order to create trustworthiness as a default? So this is a very good question, and I'm thinking about that. And I don't have any immediate answer for that. Probably you can use it as a loss function, but whether you can guarantee trustworthiness or not, it is something that I don't know. But this is a very good question, and I would love to know the answer for this question. So if you are interested, you can just reach out to me and we can explore different directions. Rather than measuring trustworthiness, are you really measuring homogeneity or generality? This is a good question. So in the sense of trustworthiness, so initially I defined the trustworthiness as so this is becoming a philosophical question probably. So here really this is my definition of trustworthiness. So if a model follows this definition, then I'm going to call it trustworthy. Otherwise, it is not going to be trustworthy. But whether we want to call this a specific definition, the definition of trustworthiness or not, this is something that probably we can discuss. All right, so I think this is all of the questions that I got in the Q&A. But if you are interested to use this KiTE package, I would be more than happy to provide the code to you. Just feel free to reach out to me and we can chat about your project, and I would be happy to provide a version of the code to you. Otherwise, in a few months from now, it is going to be public and it is going to be open source.
Thank you so much, Arya. That was a very nice presentation. And I look forward to seeing all of you next week for a presentation by Misty Hagenes from the Census Bureau.
Yeah, thank you.
Bye-bye.
Yeah, thank you everyone for joining.